My name is Oke Orieka with O3 Structural Studio, a structural practice based in College Station, Texas. And I am here to present an introduction to structural systems. One of the reasons why I'm doing this is because I interact with people, either contractors who are working mostly in residential, like commercial applications, who don't really need a full structural set of plans. They need to either size a beam or deal with a certain situation that, would take maybe an hour or two of my time. And they have expressed an interest in wanting to learn a little bit more about structural engineering and what it entails. And thankfully, I've been doing this. I have a bachelor's and a master's in structural engineering, and I also have practiced structural engineering for about 8 years now. And so I figured, and I've also taught structural systems to sophomores and juniors in college. And so I thought, why not just put that on YouTube and see whoever's interested can decide what they want to do. So we'll just go ahead and get into it. So structural systems. This is basically an introduction to the course, and then as we move on, we will delve into some of the topics that we are going to delve into. But this is sort of an overview of what we're going to be dealing with. So, of course, I just gave you my introduction, which is that I'm a practicing structural engineer based in College Station, Texas. Not only have I taught this course for about 3 years, I also have been involved in the design of new structures ranging from small residences and pavilions to schools and apartment complexes. I have also done a lot of renovations, some historical work, and also do a lot of inspections, for either foundation issues, framing issues, roofing issues, things of that nature. So I have a bit of experience in design, and I like to talk. So I thought here's that's a little bit about me. So what is the point? What are we even trying to do in this course? So basically, what we're trying to do is we are trying to it's going to be an introduction to principles of analyzing, designing architectural structures. Again, I have done some pedestrian bridges, but I'm not going to sit here and say I have expertise in other types of structures like highway bridges or like aeroplanes or like wind turbines. So I mean the concepts are the same, I'm sure, but in terms of the examples and the things that we are going to be using, we are going to be focused mostly on architectural structures, which are buildings. It's a fancy term for buildings. So that's what we're going to do. So, what is a structure? What is a structure? And this is something that I ask people, because people, don't really think about what a structure is, because a structure is not only applicable to buildings and bridges and all that, and foundations and all of that stuff, but it's also applicable to, I mean, when you have an exercise regimen or a diet or something, that is a structure. I mean, when you have a so there when you have a certain, an organization, and you have a hierarchy in an organization, that is a structure. So what exactly is a structure in our application? Well, a structure for us is something that supports itself and sometimes other stuff too. It's that easy. So, and one thing that you will realize, it's something, right? So it is it is a thing. It is a physical entity. So it's not like a piece of code or some sort of nebulous, it's not like literature, it's like a thing, it's a physical thing, right, that supports itself. So and what does it mean to support? What does it mean to support, right? And to me, to support something is when you have you're basically you're holding something, and then you're transferring that thing you're holding, the forces, to where it's going somewhere else. So there's a sort of flow to that. To support something, there's a flow to, you're holding something, and then you have to be supported by something. So there's a sort of accounting that goes on. And then the first rule of structural engineering, unfortunately, this is something that some people forget sometimes, is you have to be able to support yourself. I mean, the thing that you are designing has to be able to support itself first. Okay? And then we can begin to talk about other stuff too, putting some other stuff too. So it needs to be able to support itself. It needs to be able to support its own self weight in the configuration that you want it to be in. And then sometimes you might want to have it support other things. Like you might want to hang something off of it. You might want to have it as a floor member. Might want to have it as a roof member. You might want to have it in a wall. So it can do other things too. But the first rule is that it supports itself. And there's a lot of different applications for this here. I mean, obviously bridges and buildings and things of that nature. But ships, if you think about a ship is a structure because it supports itself. It has to support itself on water, and then it has to support the people and the cargo and the equipment and everything on top of that, right? Prosthetics. I mean, the prosthetic has to be able to support itself and then support the person that is using that prosthetic in whatever situation it is. A chair. I mean, if a chair can't support itself nor support you, then I mean, why do you why do you have it? And then a car. If you think about a car, the chassis of a car, that has to support itself. It has to be able to carry itself, and then it has to be able to fit you, and then it has to be able to, there's safety standards for how it behaves when it's in an accident. So this idea that it's got to support itself, and then it's got to support other stuff in certain configurations is very, very important. And really, it is the basic principle of structural engineering. So, in the architectural context, what are we really talking about here? So, I mean, I put together, this is a metal building frame, a weld up metal building frame of a building that I worked on here in College Station. And as you can see, I've put in a few things. So of course, I mean, there is terminology, and we're going to go through some of this terminology. But of course, we have A, which is a column. So we've got the columns over here. B, so we've got and let me go ahead and get, oh yeah, so we've got A, we've got the columns over there. That's a column too. And then we've got B. B is the beam, right? And you can see that it is horizontal, right? And there's stuff sitting on there. C is the foundation. So this is the foundation of it, and it's made out of a different material. So these are all steel, and then this is concrete down here. D, this guy is called a purlin, and we'll talk about purlins and why we would call that a purlin. E, that is a connection. So right there, I mean, the beam is not just out in space doing whatever. So whatever is being supported by the beam is being supported, right? And then that goes into the column. And then whatever the column is supporting, it is supported by the foundation. And then you have E, the connection of the column to the foundation, which is very important, and we'll talk about why it's important, as we go through the course. And then F is the I don't know if you can see that, but that's the X bracing, right? In that, and we'll talk about why that is in that direction, and the importance of having something at the top of your structure to kind of redistribute the load. And then so yeah, that's all the members that at least we're calling out over here. So what are we even trying to do? What is your structural engineer, or if you are the one that's designing a structure, what exactly are you trying to do? Well, there's two basic things you're trying to do over and over and over and over again. There's two basic things. First is gravity. You have to, whatever is coming down on your structure, you have to be able to support that. I mean, that is the thing that people typically think about and they remember the gravity. You have to be able to support that. But then the other thing in the context of buildings that you have to be able to think about and support is the lateral design. The lateral design. So what happens when you have forces from the other end? What would those forces be? It would be wind, earthquakes typically happen from side to side, flooding, soil, so things like that. So you not only have to have the gravity now, when you and the thing is you have to get all those loads. So it's sort of like accounting. You have to get all those loads from the top all the way down to the foundation. And this is the important thing is in gravity it's pretty easy because it's in one direction, right? But in lateral, you can see that the force is moving to the side, but the foundation is below, and so that presents a geometric problem. How do you get a force that's going this way down this way? So we'll talk about that a little bit more in this course as well. So what tools do we have? Well, we have a few tools. First, I mean, math. We got to use math, and I'm sorry, we got to use math and the reason why we have to use math is because there is a difference between a beam that is 10 feet long and a beam that's 20 feet long. And I'm sorry to the SI people, but we're going to be using US customary in this class. I'm sorry, but yeah, there's a difference between a beam that is 10 feet long and a beam that is 20 feet long. There's a difference between a wall that is 8 foot tall and a wall that is 25 foot tall. So how do we know the difference? It's through arithmetic, through discussing the numbers, right? And then we also have to figure out, when is a beam overstressed? Well, there's a reason, if you are below X, you're fine. If you're above X, you're not fine, and so the numbers are very, very important. Algebra as well, because we have some formulas that we're going to be able to, some things have been resolved into formulas to where you can plug and play certain things. And then angles too. Angles are very important. And again, very important when you're talking about that lateral situation where you're going from the side and you have to come down. So angles, very, very important. Physics, we're going to have to talk about physics, and that's the thing, is because some things are heavier and will cause more damage than others. We have to talk about what is exactly happening not only to the structure but within the structure, because again, these are physical. This is stuff. This is not a nebulous thing. This is an actual thing that you can physically touch and has measurements and things like that. So the physics of the matter are very, very important as well. And not only just the physics, but the material science, because there's a difference between a concrete beam of a certain size and a 2x4, right? So what is the difference? Well, first of all, it's a 12 by 36 inch concrete beam is very different from a 2x4, and you would not want to use them. If you need a 12 by 36 concrete beam and you put in a 2x4, you're gonna screw yourself. So the materials, what it's made out of, and the configuration of it. So why would you choose an I-beam? What is it about the shape of an eye as opposed to a rectangle, as opposed to some other sort of nebulous thing? So we're going to discuss that in terms of the material science of it and how the material is distributed in the thing that you are investigating. Of course, we're going to have to read, and we're going to have to read because there's rules and there's resources that, we're going to have to explore in order to find out what to do. Because again, this is a practice, and there's an accepted way of doing certain things. And so we're going to talk about those resources. We're going to talk about the building code. We're going to talk about, material codes, and things that you have to meet to be able to say, okay, this is safe. Because, and this is the other thing about buildings that is particularly fun and interesting. You don't get prototypes. You don't, you know, I've never in my life been asked to make a prototype of a building and figure out all the kinks before we actually do the building. So, but we live in a society where it is not fashionable to um, walk into a building and be like, who built this? Oh gosh, you know, like, is this safe? Is that safe? When you walk into a building, you know, you sort of assume that it's safe. And this, if you think about it, that is a very wild, you know, sociological thing, you know, that we walk into buildings and we just assume that they're safe. And that is because we have decided on certain rules as to how to do this to where we can get a pretty good product all the time, even in the most difficult architectural situations. So reading, very important. And then common sense. And if it looks wrong, it is wrong. And I will tell you, there's been a lot of times where, you know, I mean, as a structural engineer, you think that you know everything, but there's been some times when you will have a contractor that will call you and be like, this doesn't look right. And when you get a call from a contractor saying this doesn't look right, you better get your butt on site immediately. So if it looks wrong, it is wrong. There is a bit of common sense. You know, you can do all the fanciful, and that's the other problem is when you graduate and you've got your fancy degree and all of that, you know how to click through a computer and you know how to work Excel. You think that you've got it all figured out, but sometimes it just takes some common sense to be able to navigate some of these situations. So we're going to use a lot of common sense as well. So some of the things we're going to discuss in this class is supports. What is a support and the different types of supports and how, you know, how those supports act. You know, there's three main types of support. And again, we will go through this. We'll have an entire class on this particular situation. But the different types of support, because the different types of supports will dictate what is happening to the member. Because again, what is a structure? A structure is something that supports itself and other stuff too. So the support of it is also important. Not only the thing that you are supporting, the thing that is being support that is doing the supporting, but the supports also really matter as well. And then the configuration of the member is very important. So we're going to go through a bunch of members right now. We're going to start with beams. And you know, I've had you know, bless their hearts, some people point at something and say a beam or a column or whatever. A beam and a column are different things. A beam is a horizontal member that acts by bending. So when something it bends, you know, I've got a little flexo beam here. So bending, it bends. It bends that way, right? So when a horizontal member acts primarily by bending, that we would call that a beam, right? And there's a lot of different names for beams, right? So if we, when you hear the term girder, we're talking about a beam that supports other beams. When you hear joist, so a joist is just a beam at a consistent spacing, right? And so like floor joists, roof joists, things of that nature. A rafter is a joist. So a joist is a beam that is at a consistent spacing. A rafter is a joist that is running parallel to the roof slope. So parallel to the roof slope. A purlin is a joist that is running perpendicular to the roof slope, perpendicular. A spandrel beam, so spandrel just means perimeter. It's a beam on the perimeter of the building. A header is a beam above an opening. A lintel is typically a masonry beam above a building, or it is that steel member that is holding the masonry veneer, you know. And so the masonry beam is structural in the first part of it, or the steel beam that is holding masonry veneer. So veneer is not structural, it's just cladding on the building. So if you go look above your garage or above your windows, you will find a little steel angle right there. And so that is what is holding the brick up above your opening. that is also called a lintel as well. So it typically has to do with masonry. Lintel is a header in a masonry context. And then a grade beam is a foundation beam at grade. So grade is at the ground, grade. So, and we do that because grading, is when you move the ground to, and you slope the ground. So grade beam at grade. Columns, any vertical member, vertical, so it's got to be vertical, that acts primarily in compression. So you're compressing it primarily in compression. Now we're only going to deal with uh, um, columns in this situation because there are some times when the columns can also bend, and in fact, columns bend a lot, a lot. And in that situation, we call them beam columns. But we won't really, we're gonna leave that aside for now and just talk about columns in that work primarily with compression. Now, a post is a column that doesn't support a lot of load, and what you will, I think OSHA actually has a what do you call it, uh, um, a definition, and it's like a post is a column that holds below 200 pounds or 400 pounds or whatever it is. But yeah, so that's it. But columns are just vertical members. Frames are combinations of beams, columns, braces. So it comes in a frame. So you can't just have a beam that's floating off in La La Land. You gotta have it connected to a column or a wall, something, because again, what's the point? Is to get it down to the foundation. So combinations of beams, columns, you can have braces in these frames, you can have rods, you can have cables, you can have all sorts of things. Then you have walls. Walls are um, basically vertical. They're vertical. If you take a column and you just spread it over several linear feet, that's a wall. So a wall is a vertical. It's a vertical plate or shell. The way I like to think of it is a plate or it's a shell. You know, um, and so it's vertical typically. You can put axial loads on it. Axial loads are loads that are in the axis of whatever member it is that you are dealing with. So you can put axial loads on it, but it can also bend. Walls can also bend, and they do a lot. And then not only can it bend, but it can also shear, right? And it can also shear. And I'm reaching for a piece of paper here because I want to show you what shearing means. So when it shears, that's when you can see that I'm tugging on the side, like it's literally shearing. So that's that it can shear, and that's what a shear wall does. And we'll talk about that a little bit more in this class as well, the different types of walls and how they act. Then you have decks. Decks are basically walls that are horizontal. So if you take a beam and you just extend it all the way, that's a deck. And they support out of plane load. So out of plane, so this is the plane. This is the plane of the deck. Out of plane load is when you stack something on top of that and it's got to bend, outside of its plane. So out of plane loads, it can also, and then it typically transfers forces to whatever's supporting that deck underneath. Um, and then you have trusses. So trusses are, members that are connected at the points to transfer a whole bunch of loads. And there's a whole bunch of different types of trusses. You can get roof trusses, you can get bridge trusses, you can get floor trusses, you can get all sorts of different types of trusses. So trusses are also very useful structural member as well. Cables and ties. Cables are basically, and it's pushing rope. So anything that you can pull on, but you can't push on. Think of rope, think of, metal, cables, things of that nature, but it's something you can pull on, but you can't push. That's a cable. A tie is what we would call something that you can pull on and you can push on a little bit, but you don't really want to do it a whole bunch because it's very, very skinny. So it's not quite a rope, and you use primarily in tension, which is pulling, but has a small amount of stiffness. And then an arch, of course, is a compression only member. So the way the arches work is they when you stack stuff on an arch, it literally it squeezes it and makes it even stronger. So cables, ties, and arches. So those are special things that we might talk about a little bit in this class as well. Then we have foundation slabs, of course. Foundation slabs, which is just a deck with a bunch of beams that can be supported by soil, which would be called a slab on grade, or structurally suspended from the ground, which would be called a structural slab. You will hear the term structural slab, and that will have void boxes, or a crawl space. You might need some form work to be able to do that, and to be able to make that work. The difference between and yeah, we'll talk about all that when we get to foundations. Then we have shallow foundation. Shallow foundation, to me, a shallow foundation is anything that is within the top 5 feet of the soil. And so spread footings, which are footings that are under a point load, like a column. We could also have strip footings, which are spread footings that are under a wall. So a strip instead of just one point. And then we have grade beams, because what is a grade beam? A grade beam is just a narrow strip footing. So shallow foundations within the top 5 feet. And we have deep foundations. Deep foundations, we're talking about piers, we're talking about piles, we're talking about helical piers. So that's when you got to go deep to be able to get to a suitable layer to put your building on, or to anchor your building. So that's a deep foundation. And then we have site civil and industrial structures. So we're not really going to talk about a lot of civil and industrial structures. We're going to talk about retaining walls, but there's other types of things, structures. There's sheet pile walls, there's lift stations, there's storage tanks, there's pipelines, there's, all sorts. I mean, there's wind turbines, there's water retention tanks for water, wastewater treatment plants. There's, all sorts of different types of structures. There's a whole bunch of other stuff, but we're going to talk a little bit about retaining walls out of all of that, site, civil, and industrial structures. So again, what is this class about? This class is really about an overview. It's an overview of structural systems. It is also how to design these systems out of common structural materials. So basically, we're going to talk about we're going to talk about how do you figure out what you need, and then how do you figure out what you got, by saying, okay, I need a 2x6 here. How do you know that you need a 2x6? And then how do you know that a 2x6 or a 12 by 36 concrete beam or a W12 by 14, how do you know that that is what you need, and how do you know that it is adequate, right? I'll just simplify, structural engineering is about sizing. It's about figuring out what you need, figuring out what you got, and making sure what you got has more capacity than what you need, basically. And that's how you know you're fine. So you got to figure out what you need, you got to figure out what you got, and then you got to compare and say, okay, what I've got is stronger than what I need. And then, and that's it. And then also, you have to make sure what you've designed is what is built, because sometimes communication is lossy. So we have drawings, which I've never seen a perfect set of drawings in my entire life. And so when you have an idea of what you are trying to communicate, you also need to make sure that whoever is building it understands what you're trying to do. If not, bad things can happen. So we're going to cover those three things. What is this class not about? This class is not about making you a practicing structural engineer. It's not about that. It's not about that at all. It's about giving you the tools to get a basic idea of what we are doing. But again, there's, of course, the devil's in the details. So, in a lot of situations, you will need a practicing structural engineer, but in some situations, you might be able to figure it out. So this class is about giving you an overview, so at least we're speaking the same language. And so that's what's going on.